Swayam Prabha. Digital India. Educated India.
In the last three lectures, we looked at the proxies of the boundary layer flow model, namely the Stefan flow model, the Couette flow model, and the Reynolds flow model, the last one being the algebraic model. Whereas the Stefan and Couette flow models were one-dimensional models. Now we look at the complete two-dimensional boundary layer flow model so as to recover some ideas as to why we expect the simpler models to mimic the boundary layer flow model. So in this lecture I will introduce some definitions and then of course look at the governing equations and then of course we will convert them to conserved property forms for all types of mass transfer problems, and then the main important thing is we will recover the boundary conditions from mass conservation principle and the energy conservation, and ultimately we will show that NW is equal to GB for small and large mass transfer rates. So the definition of the boundary layer flow model is as follows. Here is a surface and this is the considered phase and this is the neighboring phase, as you know. This is the interface, and in the considered phase you have there may be presence of chemical reactions, there may be presence of turbulence, concentration gradients, temperature gradients, and so on and so forth. Infinity state is one where all the gradients vanish. The total mass transfer, that is both convective plus diffusive mass transfer, takes place at the interface from the neighboring phase. And in the deep inside the neighboring phase we define a T state, which of course where the concentration gradients and temperature gradients, as again like infinity state, here again in the T state they are zero, or we say that the fluid properties are uniform. So convective mass transfer takes place due to concentration gradients in the considered phase, and since the Reynolds flow model mimics the real flow, the interface mass flux is given is NW is NW equal to GB, and NW and G have the same unit. NW is required as a boundary condition because it to the mass transfer equation as well as the energy equation and as well as the momentum equation, because NW brings with it a certain velocity at which the mass comes in. So assuming steady state mass transfer, now you have d by dx of rho mu psi plus d by dy of rho mv psi plus d by dy of gamma psi d psi by dy plus a source term where psi is any property. Like when it is 1 we get bulk mass equation because that term is 0 and SW is specified as 0, and that being 1 you simply get d rho mu by dx plus d rho mv by dy equal to 0, and that is the bulk mass equation under steady state. If I say psi is equal to u, then gamma psi would be mu m effective, assuming there is turbulent flow, and S psi would be usually minus dp by dx, which is the pressure gradient. If psi is equal to omega k, then gamma psi, as you know, would be rho md effective plus equal to and source would be rk, which is the species transfer equation. Then there would be the element transfer equation, for which the source is always 0 because element alpha is a conserved property, and Hm is the mixture enthalpy. That would have a source term comprising mass transfer due to diffusion flux m double dash yk. The source, there can be other sources like dP, dt, q, rad, and many other sources. These are all ignored. We also ignored the viscous dissipation here, and all equations are coupled requiring numerical solutions. Simplifications of omega k and hm equations are possible under certain assumptions so that they are rendered to a conserved property equation. We have gone over all these processes of converting omega k and hm equations to conserved property forms in variety of mass transfer problems. So if I write in conserved property form, the equation is simply this, with S phi equal to 0, Nw equal to Gb, and B is equal to psi infinity minus psi W over psi W minus psi T. Now in inert mass transfer without heat transfer, as you will recall, psi is simply omega of the vapor and gamma is rho md, the diffusivity. In inert mass transfer with heat transfer, psi equal to omega v as an hm, and where it is an energy equation, and we make use of the assumption of Lewis number equal to 1, that is gamma mh equal to rho md plus equal to rho m alpha m. In mass transfer with simple chemical reaction, we choose psi appropriately as a combination of fuel and oxygen, or fuel and product, and so on and so forth, and hm, and again make the Lewis number equal to 1 assumption, and also say that the specific heats are equal. That is what renders the energy equation in the conserved property form. And in mass transfer with arbitrary chemical reaction, of course psi is again formed from appropriate combinations of eta alpha, and gamma m is rho md. In each case we need boundary conditions at y equal to 0, which will come from that form of the Reynolds flow model. So for the inert mass transfer, consider mass conservation between T and W states. As you will recall, this is our WW state, this is T state, and this is the infinity state, and we specify NW here, NW here. Then you will see that the mass which is coming in here is NW omega k at T, and what is going out is NW times omega k at W, and minus the diffusion mass transfer, which is rho m diffusivity omega k by dy at y equal to 0. So this would be the mass balance, because this is the multiplied by omega k will be the convective transfer, and diffusion transfer will be m dot k at W, which is nothing but from Fick's law. This is rho m diffusivity into omega k dy at y equal to 0. So if I rearrange this equation, take NW common out here, then I get the form NW is equal to rho md omega k dy at wall divided by omega k W minus omega k at T. Likewise, for any other conserved property phi, I have the same equation as you can see here, and NW will be rho md omega d phi by dy at W, phi W minus phi T, where phi would be, as you will recall, omega fu minus omega O2 divided by RST equal to omega fu plus omega product by 1 plus RST for a simple chemical reaction, and phi can be any linear combination of eta alpha, and you choose A alpha suitably for a given problem, as we indicated last time. Now these are the boundary conditions derived from mass conservation principle. Likewise, we can do so for the energy equation. So for example, in the energy equation, again, if I consider this to be WW and this to be TT state, then NW times HMT will be the flux coming in, as well as QW will be another flux coming in, whereas what is going out is the convective flux NWHW plus M dot W diffusion of the WK HK sigma. So if I equate the influxes with outgoing fluxes, I would get the form which I show here. So this is the incoming flux, QW is also the incoming flux, which should be on this side, and NW is equal to HMW, and this is the diffusion flux of species K multiplied by the enthalpy that goes with it of the species K. Now QW is equal to Km dt dy, because QW is shown inwards, and that would be equal to Cpm gamma h, where gamma h is rho m alpha m dt by dy at the W, and hence NW would be written as sigma k gamma m d omega k by dy at WHK plus Cpm gamma h dt by dy at W HMW minus HMT. And this is the general energy conservation principle. The final form of the numerator will depend on the mass transfer application at hand. So let us see what are the different forms that this numerator will take in different types of mass transfer problems. So in inert mass transfer with heat transfer, and if I make the assumption of Lewis number 1 as we usually do, then gamma h will be simply equal to gamma m, and hence Cpm d gamma h dt by dy would be gamma h into Cpm is simply sigma omega k Cpk into dt by dy, and if I now absorb Cpk inside this derivative, then I get a gamma h into sigma omega k dhk by dy at W, and hence you will see that the numerator now reads as gamma m into sigma k d omega k by dy gamma WHK plus gamma h into sigma k of omega k dhk by dy at W. But since we have assumed gamma h is equal to gamma m, this is simply the differential, these two terms are simply differentials of a product omega k hk dy at W. Summation of omega k hk is simply gamma mh dhm by dy W over hm minus hmt, hmw minus hmt. So NW takes the same form as derived from the mass conservation principle, but with the variable enthalpy hm. Let us see the numerator when mass transfer with heat transfer and simple chemical reaction. Now here we take Lewis number equal to 1 and also say that Cpk will be equal to Cpm, and for the moment let's say delta T stands for T minus T ref. Then we have enthalpy of the fuel would be Cpm into delta T plus omega Fu into delta Hc, that is I have associated the heat of combustion with the fuel, and therefore HO2 and H product will be simply Cpm delta T, and hence summation of sigma gamma m d omega k by dy hk would simply amount to gamma m dfu by dy at the wall multiplied by dhc, because the other quantities Cpm delta T, if I substitute Cpm delta T for all the three species, it will simply give me Cpm delta T gamma h into summation of d omega k by dy at W equal to 0, because summation of sigma omega k is 1. And likewise Cpm gamma h dt by dy would be gamma h dhm by dy at W from this relationship minus gamma h dhc by dfu by dy. So again you see that the addition of this term with the summation of these two terms, this term and this term, would amount to would amount to this term will cancel with this term because gamma m is equal to gamma h, and therefore we get NW again is equal to gamma mh dhm by dy at W divided by HMW minus HMT. So even in simple chemical reaction, with these assumptions of equal Lewis number equal to 1 and equal specific heats, we recover the same form as we had done earlier with inert mass transfer with heat transfer. Finally, let us look at single component convective mass transfer. Now in this case omega k is equal to 1, therefore this part of the numerator will be 0, and Cpm gamma h dt by dy would be simply gamma h, because I can multiply Cpm is inside this, and therefore that will give me hm by dy at W, and hence I get Nw equal to dhm by dy W HMW minus HMT, which is again what we had earlier. Single component convective heat transfer means supposing I have a boundary layer formed with air, I am injecting in it air itself from the wall at a given rate. So the energy equation would take the form that I have shown here. Now if I further make the assumption that the specific heats do not vary between W, T and infinity states, then of course I can make the assumption, I can show that NW will be equal to gamma H into dt by dy W divided by TW minus TT. Thus in all cases of mass transfer, mass and energy conservation principles give identical formula for NW, and combining with Reynolds flow model, which claims to mimic the real boundary layer flow model, we can say that NW will be equal to gamma psi d psi by dy W over psi W minus psi T, which we have just now derived, is equal to G times B, and that must equal rho mVW. So you can see now that the momentum equations which require this quantity are coupled with the mass fraction and energy equations through these quantities. What it shows is that the rate of mass transfer would be proportional to psi infinity minus psi W. It will also be proportional to the gradient of psi at the wall, and it will be proportional to VW, which is from that. This shows that even if gamma is uniform, the psi equation is non-linear. The gamma is the property. So even if it was uniform through the considered phase, the psi equation is non-linear because velocity field uv is a function of VW and psi infinity minus psi W. Now this kind of coupling through the boundary conditions of momentum and the mass scalar equations is akin to the natural convection problem, in which U and V are coupled to the energy equation through the source terms we call the buoyancy term. So in natural convection, momentum and energy equations are coupled through through buoyancy source terms, whereas in mass transfer the coupling arises because of the boundary condition at the wall. This is the difference between a natural convection problem and a forced convection mass transfer problem. So the coupling between the momentum and psi equations can be ignored when NW, which is proportional to VW, tends to 0, which means if the mass transfer rate is very, very small, then we can say that G star, which is the value of G at for small mass transfer rates, then NW divided by B psi NW tends to 0 would be minus gamma psi d omega by dy divided by W psi W minus psi infinity. This follows from the previous equation which I have shown here. So I have simply cancelled psi W minus psi W minus psi T, and this is psi infinity minus psi W is taken to the denominator. So you get G star is equal to this quantity. So the G star now depends only on the psi profiles and not on the boundary condition, because VW is tending to 0. This definition is analogous to that used to define the heat transfer coefficient. As you will recall, we define the heat transfer coefficient as minus k dt dy tw minus t infinity. So likewise we say that the g star, which is the mass transfer coefficient at vw equal to 0, is gamma minus gamma psi d psi by dy at w divided by psi w minus psi infinity. So the two definitions are now analogous, and now you can see why we have been calling g as the mass transfer coefficient. When NW is large, the coupling between the momentum equations and the psi equation is strong, and NW equal to g times b psi. Hence, g must be a function of b psi and g star equal to g when b psi tends to 0. Yes, g star is simply g where with b psi tending to 0, but it would also, g will also be itself be a function of g, and perhaps even of Reynolds number, Prandtl number, and so on and so forth, but we shall shortly see what the state of affairs are. By analyzing experimental data on mass transfer with and without combustion, Spaulding showed that within experimental scatter, g by g star is equal to nw by b divided by nw by b as at very, very small mass transfer rates is in fact equal to fb only. This is worth noting, fb only. In other words, the equation shows that g over g star is not influenced by Reynolds number, Prandtl number, or Schmidt numbers. This is what the experimental data shows, both in internal flows as well as external flows. Flow over cylinder, flow over flat plates, and flow through the tubes, and so on and so forth. It may be a problem of evaporation, it may be a problem of condensation, it may be a problem of combustion. All these problems for which experimental data were available, Spaulding showed that g over g star turns within experimental scatter, say about plus minus 10 to 15%, g by g star is a function of b only, which is a remarkable result, that this ratio should not be influenced by any other quantity other than the driving force b. So it's independent of Reynolds, Prandtl, and Schmidt numbers. So all that we would require now is that is the value of g star evaluated from h cof vw equal to 0 divided by cpm, and fb to obtain g. So what are the forms of FB? And that's what we want to find out. Incidentally, this book, Spaulding DB, Convective Mass Transfer, published in 1963, is a pioneering book on mass transfer, and particularly of great relevance to engineering community. So now let us see what the form of FB should be. So using computer simulations of the boundary layer equations as well as experimental data, Spaulding showed that g over g star is equal to fb, and that function fb is nothing but ln 1 plus b by b. Now if you'll recall, this is the relationship which we had also predicted using Stefan flow model as well as the Couette flow models. Of course, Stefan flow model was for diffusion mass transfer only, whereas the Couette flow model was for included convection in its fold, and therefore this relationship is unique. It doesn't contain any Reynolds number, Prandtl number, or anything like that. We take up the issue as to whether this relationship can actually be can also be derived from the Reynolds flow model, just as we had shown that it mathematically that the Stefan and Couette flow models yield that relationship. So in order to do that, let us reconsider our T state, W state, and the infinity state with the considered phase shown here between W and infinity state. Now here what I've done is, let us consider an elemental strip here of thickness delta y. The outer edge of that strip is yo, the inner edge of that strip is yi. And let us postulate G star star as a flux. at the YO surface, which is coming in and bringing with it the properties of the YO surface. And likewise, NW plus G star star is an outgoing flux which brings with it the properties of the YI state. So this is what I've said here. G star star crosses the YO surface carrying properties of the YO surface, and similarly the Reynolds flux G star star plus NW crosses YO surface carrying with it properties of the YI surface. The physical idea behind introduction of G star star is that the real flow processes like heat conduction, mass diffusion, turbulence, etc. do behave like the Reynolds flow, but on a much smaller scale, delta Y, YO minus YI tending to 0. So if I now write the mass conservation over YO and T states, then NW psi T would be the incoming flux plus G star star into psi times YO would be the incoming flux from YO surface, and that would equal G star star plus NW into psi YI, and therefore this would rearrangement of this would give me NW divided by G star star is equal to psi YO minus psi YI divided by psi YI minus psi T, or this difference is nothing but d psi Y, and this is psi Y minus psi T. So if we consider large numbers of delta Y between 0 and delta of the considered phase, or between infinity and W states, then simply NW into summation of 1 over G star star would amount to integration of 0 to infinity d psi Y by divided by psi Y minus psi T, and the integration would naturally yield ln 1 plus psi Y infinity minus psi W divided by psi W minus psi T, which, as you know, is nothing but b psi ln 1 plus b psi. So if I take this result further, then as b psi tends to 0, NW W into infinity 1 over G star star would simply tend to b psi itself, and so as b psi tends to 0, W to infinity G star star raised to minus 1 would tend to b psi by NW. And therefore comparison with the observation of slide 11, what was the observation we made on slide 11? G over G star is equal to NW by B over NW by B, NW0 is equal to FB. So comparison with that will show that as B psi tends to 0, the sum of G star star raised to minus 1 is nothing but the G star raised to minus 1, and hence NW equal to GB psi is equal to G star ln 1 plus B psi, and G over G star is equal to FB, and that is equal to 1 plus ln 1 plus B psi over B psi. So this is a very interesting result, that 1 over, remember G is conductance, and therefore 1 over G is resistance, and therefore the total resistance between W and infinity states which we say is 1 over G star, is nothing but sigma 1 over G star star, where G star star is the resistance of the small element G delta Y over delta Y. So we can interpret now that 1 over G star, the resistance, is the sum of the resistances to mass transfer between W and infinity states, and the inverse of that is the conductance of for mass transfer. And in other words, the ratio of the conductance at large mass transfer rates divided by conductance at small mass transfer rates or negligible mass transfer rates is simply a function of ln 1 plus b psi by b psi. This formula can be used for large mass transfer rates obtained in liquid fuel burning and in transpiration cooling, as we shall see in later lectures where I will be considering problems. Small b psi usually occurs in combustion of solid fuels, and in evaporative cooling or air conditioning and so on and so forth. But where in these applications B psi would be less than 0.1 in these applications, combustion of solid fuel and evaporative cooling and air. In fact, it will be of the order of 0.02, 0.03. Whereas in transpiration cooling and liquid fuel burning, or value of B psi can vary between 0.5 to nearly 10. So B psi can be really large in liquid fuel burning and in transpiration cooling. So we shall check how good is this formula from the analytical solutions we have derived so far for laminar flows as well as in turbulent flows, and let us see how well this formula is so that we can confidently use it at different mass transfer rate. If the mass transfer rate is very, very low, then of course there is no problem, because G by G star will be simply 1, and you would have straight away there is no difficulty. If G by G star is simply is moderate, then of course this formula will work. At very, very large mass transfer rate, remember the definition of B psi says that B psi is psi infinity minus psi w divided by psi w minus psi t. So when B psi is very large, psi infinity minus psi w is also large, and this means that when the property in the infinity state and the w state is large, we would expect the properties to vary between the w and infinity state. So any departure from this formula, if found in experiments, would be largely due to property variations, and therefore this formula is usually corrected for property variations, and that is the matter for discussion in the next lecture.